As I mentioned to Professor Sabari, that I will try to give a brief overview of the Z-scan development and impact. And sort of, I would say, the early years history of it and how it was developed. And just before I forget again, I also I just wanted to congratulate the award winners, Professor Philip and Rao in particular. I'm also familiar with Dr. Rao's work at University of Hyderabad. Anyway, so congratulations. I'm also particularly honored to give this talk at the university who's named after your famous and revolutionary poet, Bharati. Sorry if I'm not pronouncing his name, but Bharati Dasan. Anyway, let me, hopefully I don't take too much of your time. I just want to start, of course, you all know that with nonlinear optics basics, that of course, as mentioned earlier by the speakers, you have nonlinear refraction, and here you have nonlinear absorption shown. I'm showing it here by the first order. Obviously, you could have higher orders. Here is, for example, 2-photon absorption. This is optical Kerr effect on the left. And of course, the electric field, as it propagates an optical field, the intensity evolves, follows the Beer's law here, that you have linear absorption, and then here you have 2-photon absorption, for example. And of course, the phase evolves as shown here, with proportional to the change of index, which is N2 times I. So, and as also mentioned earlier, of course, the application of optical Kerr effect and nonlinear absorption, has been touted for many years, including using it for all optical switching, of course, optical solitons. Kerr lens mode locking was developed, of course, in the early 90s and uses Kerr effect, and then optical limiting, and of course on the downside there is optical damage always as a result of nonlinearities, filamentation, and so forth. And of course it's a field that is thriving, and it's progressing every year with new material. Again, how do we measure a phase? Like in optics, as we all know, that if you want to make, you cannot measure the phase directly, you have to reference this to itself, hence interference. For example, here I'm showing just a Michelson interferometer. For example, laser goes into these, splits into these two arms. And as you change the intensity, of course, one arm path length would change due to index of refraction. And you measure a signal which is proportional to absolute value of N2 times I. So these interferometers would not give you necessarily the sign of the nonlinearity, but the bottom line is that you need interference to measure the phase. Now, of course, as we all know, again, I apologize if I'm going through too much of the basics, that diffraction is nothing but interference, and that once a beam of spatially varying, like a Gaussian beam, as it propagates, different part of the beam in the far field essentially interfere, and so diffraction is interference, and that means that we can use diffraction to measure these nonlinearities. And one manifestation of these is, of course, what we call self-focusing. The fact that the nonlinearity induces a lens in the system, and then you can observe it at some distance, whether the beam narrows. Is everything okay? Do you hear my um, um, and if it is the nonlinearity is negative, then you would have self-defocusing. So we exploited this phenomena and what we call Z-scan for the lack of better name. And what we do essentially is that we monitor the transmitted beam through a material in the far field while varying the incident intensity and the phase front simultaneously. And that's essentially by scanning this here, we change not only the intensity as it scans, but also the phase front, because the phase front changes simultaneously. And of course, rather than monitoring the beam profile, it's best to just put an aperture there, and that makes it very simple. Now, that's why I wanted to share my screen. I hope this animation works. If not, please give me a clue and I would stop it, because I know it's rather, the reason is that these flash animations no longer you can embed them in PowerPoint. So yeah, this is an animation that I had, a student of mine had made, and essentially what I am showing here is the transmission through the aperture in the lower graph. And as you scan the sample, for example, here I'm assuming a positive nonlinearity. As you scan it and get closer to the focus, the beam, of course, focuses in the near field, but in the far field, it diverges, and hence the intensity decreases. And then it becomes a reduction of the transmission through the pinhole. As you move it through, then it goes, the beam, a positive lens after the focus tends to recollimate the beam, and that would increase the intensity through the pinhole, and you would have an increase. And then as you move on, you would have go back to the linear regime. So a typical Z-scan for a positive nonlinearity would be a valley followed by a peak. If you change the sign of nonlinearity, this would change sign as well. And then that means a nonlinearity, a negative nonlinearity signature, Z-scan signature would be a peak followed by a valley as we scan it through here. Now, notice that if I remove the aperture and what we call an open aperture, then nothing happens, because essentially if you have purely refractive nonlinearity, the beam narrowing and broadening, if you integrate the intensity, nothing happens. But if you have a two-photon absorption, then as you change, scan the sample and go through the focus, at the focus, you would have very large absorption change that would result in a dip in the absorption. And of course, if you have saturation of absorption, it would be the other way, it would be upward. So this is a positive, beta being positive. Now, of course, if you all at the same time, then you close the aperture, then your Z-scan trace looks like this. It's lopsided with the negative nonlinearity, with the positive nonlinearity is the other way around. Bottom line is that with these, you can measure not only the real and imaginary part, in other words, the absorption and refractive nonlinearity, but also you measure the sign. And that's why this thing was very nice and simple. So, and that's why these papers that we published, the first one was in 1990, and a more comprehensive paper was in, actually the first one was 89, and then the next one was in 1990. And here is a picture of, that's the graduate student, Ali Saeed, who was working with me in the lab. That's Eric Van Strylen, and that's myself when we had a lot more hair and less grayer. and rather much younger. But in any case, and that's these two papers collectively have been cited a lot. The reason I'm putting here, not necessarily not to brag, saying I'm trying to say that the reason these papers have been cited a lot and have been quite popular is simply because of its simplicity in both implementation and analysis. Because as I showed, you can not only get these, all you need is a lens and a translation state and an aperture essentially, and of course detectors. And then analysis is very simple because with a very simple formula, or even if you don't use the formula, once you measure the peak and valley, the separation is this simple expression would give your nonlinear phase shift on axis, which is proportional to your N2 and times intensity. And also the separation between peak and valley is roughly 1.7 times the Rayleigh range given by this. So that means this is absolutely calibratable. Even if you don't know your beam spot size, by measuring this separation, you will know your Rayleigh range, then you would know your spot size. If you measure your power or energy in the pulse or in your laser, then you would know already what's your intensity. And from here, you would know your phase shift and you back up, calculate your N2. And also, of course, once you have a nonlinear absorption, then you you would have this simple expression that you can use, right? And here S is the aperture transmission. So that's what it's been simple, and for that reason, what I once called in one of my talks that it brought nonlinear optics to the masses because it's such a simple setup and can be both simply implemented and analyzed. Now, since then, there's been a lot of work, including some, of course, in your colleagues there. For example, is the Excite probe two-color Z-scan, time resolved. I will mention some of these things in a little bit more detail, what we call eclipsing Z-scan, top hat Z-scan, thick medium Z-scan, and high-order nonlinearities that Professor Van Strylen would cover later in more detail, I hope. Also, lately, again, there is Kerr-lens autocorrelation, thermal lens absorption spectroscopy, and white light continuum Z-scan, and so forth. Again, I'm just mentioning things that what I would call in early days. I necessarily have not caught up necessarily myself with the literature, unfortunately. For example, what I just wanted to give you some examples of what we call thick medium Z-scan. When the length is much larger than the Rayleigh range, then your Z-scan trace is no longer just a peak quickly followed by a valley or the other way around. But now in this case, once you do your scan, the peak and valley correspond to focusing at the surfaces of your material. And in between, they cancel each other and it becomes a flat region. And of course, if you have very long material, then it becomes flat very flat towards the center. And you can also derive very simple expression for analysis of this, right? And the next thing is a graduate student, when I was at Creole, Tijen Zhao, came up with this idea, which we called eclipsing Z-scan. And rather than putting an aperture here, you can put a obstruction disk here. And that's why we call it eclipsing Z-scan, because what you're measuring here is the spillover of the intensity that spills over. And that turns out to be much more also sensitive, also not absolutely calibratable, but if you want to measure it has very high sensitivity. It has actually 10 times more sensitivity than regular Z-scan. Another, of course, I mentioned earlier, you can have then excite probe Z-scan, which means one beam excite would form the lens and the probe would probe it, and then you can switch these around. Now this can be done both in terms of in CW or pulse, and then you can also do time resolve and look at the dynamics of the nonlinearity. And there is a series of paper both by us and by the Brazilian group that on that. When I moved to Orlando, also moved to New Mexico, also developed this what I call care lens autocorrelation based on the Z-scan technique for measuring the pulse duration of femtosecond pulses and also measuring the nonlinearities in many materials which very high sensitivity and time resolve them. I'm not going to go through the details. Now, at the end, what I want to talk about, as I mentioned, what was the impact of this technique, at least in early days. One thing, the first thing was that it led us to a good understanding of the electronic Kerr effect and two-photon absorption in optical solids and semiconductors, and in the relation between the two. And I'm going to briefly go through that. And that right after we developed Z-scan, for example, we are looking at zinc selenide. And zinc selenide, we noticed that depending on the wavelength, we could either get this curve, which is a negative nonlinearity, or the other one with solid with a positive nonlinearity. And then positive nonlinearity was at 1 micron, which was the two photons. In other words, you don't have any two photon absorption. But when you went to the 532 in the green wavelength, then because you had two photon absorption, the nonlinearity changed sign, the N2. And that was, for the first time, we could measure the dispersion of these nonlinearities accurately. And also, of course, that was the open aperture data. So that led us to believe that there must be some dispersion relation, very similar to Kramer's chronic relationship in linear optics, that relates the refractive index to absorption, that there should be a nonlinear Kramer's chronic relationship between these. Of course, there was a lot in the literature, but I'm going to skip the details and say that led us to this theory that we managed to calculate, and this was in 1991 as well, that we developed a theory that was related Kerr effect to the two photon absorption, and it led to a simple formula, a very analytic formula using two parabolic band model and using quantum mechanical calculation, that we could get not only the dispersion function, G2, but also the band gap scaling. And this simple model not only predicted the dispersion, in other words, here is all these materials, zinc selenide, cat sulfide, again, zinc selenide, that's again that zinc selenide, these are the two zinc selenide that I showed you. And all of these different materials at different wavelengths fitted this curve very nicely, even down here, I'm not showing it. And also the band gap scaling in almost 6 orders of magnitude fitted this simple expression, not only in glasses and optical solids, but also small gap semiconductors. And again, Eric later on is going to show you maybe more, because they did more, also use white light continuum Z-scan that showed this dispersion for a simple one material very carefully. Another impact was what we call optical switching scaling laws, because for optical switching, obviously, you need very large N2. At the same time, you want to have very small beta. You don't want to have losses. You don't want to have not only linear losses, you don't want to have nonlinear losses. That means if the figure of merit for that is N2 divided by beta. And if we put it in that theory, we can calculate this and fit it with the data, that existing data. Essentially, well, it tells that in optical switching, there is no free lunch. Either if you want to do optical switching, for example, this is for nonlinear directional couplers, and this is for fabric Pro, that figure of merit that is needed. You have to go just below the half band gap, use the materials here, or go very close to the band gap. But the problem here that you have a lot of linear absorption. So essentially that was put limitations on optical limiting in optical switching in semiconductors, all right? And lastly, what I want to talk about is that Z-scan also led us to the discovering and understanding of cascading second order nonlinearities, what is known as Chi2. And the experiment that was done, we essentially were doing KTP, which is nonlinear crystal known for its second harmonic generation. We were scanning it both in and changing the phase matching condition. And what we find out that depending on the phase matching angle, when n of omega was larger than n of 2 omega, the second harmonic, you would have a positive nonlinearity. And in the we did this is, by the way, in the normal dispersion. And if you switch it and tilt the crystal, or however you change the phase matching, you can switch the sign of nonlinearity. And that led us to an understanding, and which fits very simple model of coupled amplitude equations. So by that, essentially, I have just wanted to cover and give you a flavor of the early days, in the 90s, of the Z-scan and its impact. Obviously, many of you, your colleagues and others in various places in the world have studied these much more, and I'm not necessarily knowledgeable of all the advances that has been done in this area on nonlinear optics. I just wanted to thank you again. I'm really honored, and I just wanted to end this with a poem by again that I found. I hope I found it right online by Bharatida-san. And again, I'm grateful to all of you for all your kindness, and I'm flattered.